Ice cubes clink in your drink, snow crunches underfoot, and glaciers tower like frozen giants. And no matter where you find it, one thing's always true. Ice is cold. But why? Why does frozen water chill us to the bone, while liquid water just feels wet? This is WhyOWhyTV, where we ask the questions everyone wonders and uncover the surprising science behind them. Let's start with the basics. Ice is simply water in its solid form. There's nothing exotic about its chemical makeup. It's still just good old H2O. But the way those molecules behave is where things get fascinating. In liquid water, at room temperature, these molecules are like a hyperactive crowd. They have a lot of energy, so they're constantly bouncing, tumbling, and sliding past one another. They form fleeting connections with their neighbors, called hydrogen bonds, but these bonds break and reform in a fraction of a second. It's a chaotic, high-energy dance. But what happens when we turn down the temperature? As the water cools, we're essentially taking kinetic energy away from these molecules. Their frantic dance begins to slow. The bounces become less energetic, the tumbles less frequent. As we approach the freezing point, 32 degrees Fahrenheit or 0 degrees Celsius, the molecules just don't have enough energy to break those hydrogen bonds and move past each other anymore. The party is winding down. At this critical point, something incredible happens. Instead of a chaotic jumble, the molecules begin to organize. They lock into place using those hydrogen bonds to form a highly ordered and stable three-dimensional pattern. This structure is a crystal lattice, and for water, its specific shape is a hexagon. This is the very reason why snowflakes have their iconic six-sided symmetry. Each one is a single, beautifully complex ice crystal, a tiny monument to molecular geometry. And here's where water reveals its most famous and, frankly, weirdest property. Unlike almost every other substance which contracts and becomes denser when it solidifies, water expands. This open hexagonal structure takes up about 9% more space than the jumbled molecules in liquid water. This lower density is precisely why ice floats. This single property is profoundly important for life on Earth. It means lakes freeze from the top down, creating an insulating layer of ice that protects the aquatic life below. This expansion also has a destructive side, as anyone with a burst pipe in winter knows. The same force reshapes landscapes through frost wedging, breaking apart massive rocks over millennia. So why does ice feel cold to us? It's not because ice is reaching out and giving you a chill, it's the opposite. Ice is stealing your heat. When you touch an ice cube, energy flows out of your warm hand into the colder ice. That energy makes some of the ice molecules vibrate more, while your skin molecules vibrate less, which your brain interprets as cold. Think of ice as a tiny thief, robbing your body of warmth one molecule at a time. The key to temperature is molecular motion. Heat is just the vibration and movement of atoms and molecules. More movement means higher temperature. Less movement means lower temperature. In ice, the molecules barely wiggle compared to liquid water. So when you touch it, your molecules slow down to match its speed. That energy transfer is what your nerves pick up as cold. An ice cube from your freezer is usually around 0 degrees Fahrenheit or 18 degrees Celsius. But ice can get much colder. On Earth, the coldest natural temperature ever recorded was negative 144 degrees Fahrenheit, negative 98 degrees Celsius, in Antarctica. Out in space, water ice can drop to hundreds of degrees below zero, sometimes below 200 degrees Celsius. And the ultimate limit is absolute zero, at 459.67 degrees Fahrenheit or 273.15 degrees Celsius. That's the point where molecules stop moving entirely. Ice never quite gets there naturally, but scientists in labs have cooled atoms to just fractions of a degree above absolute zero, as close as physics allows. Ice isn't just a party trick for your soda. It's a planetary-scale air conditioner. The vast, white polar ice caps act like giant mirrors. This is the albedo effect. Just as a white t-shirt keeps you cooler than a black one, these ice sheets reflect solar energy back into space. This reflective power is crucial in regulating Earth's temperature, preventing our planet from becoming dangerously warm. Ice also acts as a vital natural reservoir. High in the mountains, winter snowpack locks away vast amounts of water. When spring arrives, this snow melts gradually, feeding rivers that provide essential fresh water for billions of people. Then there are the glaciers, slow-moving but immensely powerful rivers of ice. Their colossal weight and grinding force are nature's master sculptors, carving out dramatic U-shaped valleys and breathtaking fjords, shaping the very mountains we see today. And of course, ice shapes our daily lives. Beyond the joy of a snowman or a cold drink, it's a cornerstone of recreation and health. It provides the surface for sports like ice hockey and figure skating. Before refrigeration, harvested ice preserved our food. Even today, a simple ice pack soothes an injury. It's a substance woven into the fabric of our culture and well-being. But the story of ice extends far beyond Earth. On Mars, the red landscape is crowned with polar caps of water ice and frozen carbon dioxide. Even more tantalizing are icy moons like Jupiter's Europa. Beneath its frozen shell, scientists believe there is a vast ocean of liquid water, warmed by the gravitational pull from its giant parent planet. We also see it in comets, the dirty snowballs of our solar system. These ancient travelers may have delivered water and organic compounds to a young Earth, potentially seeding life itself. Each discovery of space ice is a signpost, telling us where water exists, and pointing us toward the most promising places to search for life. So, let's bring it all together. We asked, why is ice cold? It's all about energy. Heat is the energy of molecular motion. In liquid water, molecules move freely, but when water freezes, they lock into a rigid crystal structure. Their energetic dance becomes a subtle vibration. When your warm hand touches ice, your heat energy rapidly transfers to the ice, trying to get its molecules moving again. Your brain interprets this sudden loss of your own heat as the sensation of cold. Essentially, ice doesn't make you cold, it just takes your heat. And ice is so much more than a frozen curiosity. It's a planetary architect. On Earth, massive glaciers carved the stunning valleys we see today, and our polar ice caps act as a global thermostat, reflecting sunlight to regulate our climate. But the influence of ice stretches across the solar system. It forms the brilliant rings of Saturn and covers the poles of Mars. Most excitingly, icy moons like Europa and Enceladus are thought to hide vast liquid oceans beneath their frozen shells, prime locations in the search for extraterrestrial life. From shaping landscapes to hinting at life beyond Earth, ice is a cosmic wonder. We hope this journey into the heart of ice has sparked your curiosity. What was the most fascinating fact you learned today? Let us know in the comments. This has been WhyOWhyTV. If you enjoyed unraveling this mystery, please give this video a like and share it with a fellow curious mind. And to make sure you never stop asking why, hit that subscribe button and ring the bell for more deep dives into the world around us. And speaking of questions, we're leaving you with one that takes us to the opposite extreme. We've explored the science of cold, where molecules slow to a near standstill. But what happens when they speed up to unimaginable levels? Our next question will take us from the freezer to the heart of a star. If ice is cold, why is the sun so incredibly hot? That's a why for another time.